Hello and welcome. In this video, we'll walk through an interactive audio signal processing application built in Python. This tool uses a graphical user interface to let us load, manipulate, and analyze audio data in real time. Whether you're studying signal processing or exploring audio analysis, this project gives you hands-on insight into how signals behave under different transformations. Let's start by understanding how the code works behind the scenes. First, several essential libraries are imported. NumPy is used for numerical operations. scipy.i.o.wav file helps us read audio files. Matplotlib.pyplot enables plotting. SoundDevice lets us play sounds directly from Python. Tkinter builds the GUI interface, and we use Figure Canvas, TKAGG, to embed our signal plots right into the application window. A series of global variables are declared. These will hold the audio signal, the sampling rate, and various processed forms of the signal, like the noisy version, the filtered output, and the error signal. The GUI window is then initialized with a title. A figure canvas is created to display our waveforms, and a label is placed below it to show numerical results, such as power, energy, and signal-to-noise ratio, or SNR. The function updatePlot draws the signal onto the canvas. It maps the amplitude of the signal over time and keeps the time and amplitude axes fixed for consistent viewing. The compute-power-energy function calculates two key properties of the signal, its average power and total energy, both of which are central to understanding signal strength and content. The calculate-SNR function compares how much of a signal remains intact compared to the noise or filtered version, producing a clear metric of quality in decibels. We also have utility functions to update the label text, playback audio, and perform each step of signal processing, such as loading, downsampling, filtering, and comparing signals. Now let's move into the practical demonstration. As you can see, we begin by loading an audio file. The waveform appears on screen, representing the original signal. It's smooth and continuous, and when played, it sounds clean. The power and energy values displayed give us a baseline for comparison. Next, we apply downsampling. Visually, the waveform appears slightly compressed, with fewer data points over time. This operation retains the shape of the original signal, but reduces its resolution. Since we've cut the number of samples in half, the total energy also drops by nearly half. This is expected, as energy is proportional to the number of samples. However, the average power stays relatively stable, because it's a measure of signal strength over time. We now move to the noise addition step. A new waveform is plotted, and you can see it's more erratic. Random fluctuations have been overlaid on top of the original signal. When we check the power and energy, both values increase, since noise contributes extra amplitude across the signal. Then, we view the different signal. This plot reveals the noise itself, the difference between the noisy signal and the original one. It's a clear visualization of what was added, isolated from the rest. Next, we apply a simple averaging filter. The resulting waveform becomes noticeably smoother. Although some of the original characteristics are restored, it's not a perfect recovery. This filter helps suppress the noise, but also slightly softens parts of the original audio. The energy decreases again, reflecting the loss of high-frequency noise components. We then look at the error signal, which shows the difference between the filtered signal and the original. The remaining deviations here represent what the filter couldn't fix. A smaller error signal means better filtering performance. Finally, we calculate the signal-to-noise ratio. The first comparison is between the original and noisy signal, and the result is relatively low, indicating that noise has strongly affected the signal. The second comparison is between the original and the filtered signal. The SNR value here is higher, showing that the filter has improved the clarity of the audio by reducing unwanted noise. Comparing the two SNR values gives us a clear sense of progress. Even though the filter didn't fully recover the original, it significantly improved the quality relative to the noisy version. And that brings us to the end of our walkthrough. This application gives us a powerful hands-on way to explore real-world signal transformations through both visuals and sound. Thank you for watching.